Well, now's as good a time as any, Mr. Newman. Take her down to periscope depth.
Yes, sir. Clear the bridge. Dive.
Stand right. Thanks.
Welcome everybody. This is Sal, and this is going to be a totally unstructured show because I'm going to be fumbling through trying to relearn my quantum mechanics. And the book that I learned quantum mechanics from is this book by David J. Griffiths. And something I should point out is that the program that I took in graduate school was for engineers, primarily for engineers who didn't have a physics undergrad degree. So it was a mix of trying to get them a little bit of undergrad education in physics and then also kind of graduate level stuff. Many of the engineers that were taking these courses worked at the Applied Physics Lab at Johns Hopkins University or in the aerospace industry. They were building, a lot of them were involved in building space probes, processing the data. So it was helpful to understand some of the physical experiments that were being carried out. So that being said, the pluses and minuses of learning things from a textbook is sometimes the plus is that you really do get things in very fine detail and you acquire new skills. The minuses are that sometimes it's just thrown at you without a lot of context. And now looking in retrospect, having taken this course almost exactly 10 years ago, which seems like yesterday, but then it is a long enough time to have forgotten an enormous amount. I'm realizing now just how much was just thrown at us, at the students without any explanation of context. There are a lot of equations just thrown and say, okay, this is your starting equation. It often wasn't explained where it came from. Even to this day, I don't completely understand where some of the ideas came from. They're just sort of accepted on faith. So I'm going to try to work through that. One of the first things I need to do is I'm going to try to get to tutorial's point. I need a latex, a means of rendering latex so you can see the equations clearly. So I'm going to really fumble through this. So I'm going to bring up just a plain Google screen. I'm going to look for a latex renderer. Someone told me the proper way to pronounce it is latex, but latex tutorials. So there's an equation editor, and I'm going to try to bring it up here. So let me see what the Schrodinger equation is supposed to look like. Now I'm going to have some comments on this. And I just found this out today. Not that I didn't know about it, perhaps in passing. There are many ways to state the same thing. And perhaps, let me see if I could find this article. It's by Ryu on Dirac. So I'm looking this up. So elements of Dirac notation by Frank Ryu. And goodness, I hope I can. I'm doing this on a second computer, and it is this other computer is really slow. I think this is one of the best descriptions, at least the opening paragraph. I haven't gone through the whole thing, so I'm just going to share it in the chat. And if you're not live, unfortunately, it takes a while for the system to catch up and show the chats during the recording, which is really kind of unfortunate. And what happened here? Goodness, I already lost. Oh dear. I already lost one of the windows that had the show on it. So now I can't even see it. If you'll give me a moment, apologies for the delay here. See, I'm going to try to go back to my channel. Told you this is going to be a fumbling session here. Here, I got it. So now I'm going to paste this in the chat. This is from Frank Ryu. See if I can find it. Frank Ryu. Okay. And maybe what I'll do is I'll actually show it on my screen, because I actually think it's going to be very helpful. Frank Ryu. So let me see if I can find it. Oop, wrong screen. Okay, see if I can. That's kind of unfortunate. I'm going to have to. I'm just still learning StreamYard. And what's kind of obnoxious is that I can't cut and paste from the chat within StreamYard. It's a really obnoxious feature. I can't pin it to the screen, as you see, but let me try to get this Dirac. I'm going to Google again, Dirac Notation, Frank Ryu, and I'm going to show it here, and I'm just going to read it because it's better that I read it and have it printed. It says, let me see if I can expand this. In the early days of quantum theory, PAM Dirac created a powerful and concise formalism for it, which is now referred to as Dirac notation or bracket notation. Two major mathematical traditions emerged in quantum mechanics: Heisenberg's matrix mechanics and Schrodinger's wave mechanics. These distinctively different computational approaches to quantum theory are formally equivalent, each with its particular strengths in certain applications. Heisenberg's variation, as its name suggests, is based on matrix and vector algebra, while Schrodinger's approach requires integral and differential calculus. Dirac's notation can be used in a first step, in which the quantum mechanical calculation is described or set up. After this is done, one chooses either matrix or wave mechanics to complete the calculation, depending on which method is computationally most expedient. Amazingly, this was mentioned in passing in my physics classes about Dirac, Heisenberg, and Schrodinger having equivalent formulations. Nowhere was it so nicely stated how they related to each other. And why I kept seeing bracket notation used by so many physicists, and yet in the book by Griffiths, it was only treated with one page, and I was just like, to my horror, it's like that's kind of disappointing that I hardly saw any bracket notation in my book. So let me, as I try to struggle through this, let me try to explain my understanding of Schrodinger's equation. But I found this really good article in New Scientist if we want to answer the question, what is quantum mechanics? So let me look this up. This is one of the best. I think this is one of the best explanations I've seen, and I wish it had been covered in class on the first day. So it says here, and this is the title of the article, Quantum Physics from New Scientist, our best basic picture of how particles interact to make the world. It says here, what is quantum physics? Put simply, it's the physics that explains how everything works. The best description we have of the nature of the particles that make up matter and the forces with which they interact. Quantum physics underlies how atoms work, and so why chemistry and biology work as they do. You, me, and the gatepost, at some level at least, we're all dancing to the quantum tune. If you want to explain how electrons move through a computer chip, how photons of light get turned into electrical current in a solar panel, or amplify themselves in a laser, or even just how the sun keeps burning, you'll need to use quantum physics. Oh, hello, Speed of Sound. It'd be great. Great to see you, brother. if you want to join the stream and just shoot the breeze here as I fumble through this, like our classes, I'm putting a link just for you. There you go. So the difficulty, and for physicists, the fun starts here. To begin with, there is no single quantum theory.
Hello.
Man, great to see you.
Yeah. Well, did you have Dr. Dan or Ron on just now? Ron Garrett?
No.
Oh, I thought you did. I must have been looking at something else. But
that was an old recording.
Oh, okay. You're playing.
of our debate. And so I'm just kind of fumbling through this. I got my, I had to go to the basement. I got my book, but that's been in my library. Let me show you something.
Is that? Yeah, I have that too. Let's see. Where is it? Hang on a second. Let me see if I can find mine. So I got the 3rd edition. Which one is that?
The 2nd edition.
Okay.
And I took my class in 2010.
Yep.
And I got, this is my notebook from my class with my homework assignments. And I really hope the solutions are out there somewhere. And, when you're taking class, the professor doesn't want you to have access to the solution, so you don't just copy it and submit it as your homework. But in the process of self-teaching, it's like, I'd like to know that I did the homeworks correctly.
That you did it right. Yeah, solution manuals are very important if you can get them, but I bet I could find them.
I bet you can.
Yeah.
If any guy can find it for Griffiths. And so I was just kind of rambling on what I didn't know about. It's really embarrassing. I got my degree in physics, and if someone asked me like a basic question, it's like, what's physics? And it's like, I don't know.
Yeah.
Like I took information and communication theory. If someone asked me what's information, it's like, that's really funny. They never defined it.
No.
So there's a lot of things. It's like, okay, what's chemistry? And just like, so it's kind of nice after class you get to ask these kind of more kind of like overview questions, because you don't see the forest through the trees when you're taking these classes. You're just throwing at it. It's just stuff down your throat as fast as possible, and you don't know.
That's why if I audit a class and don't even attempt to take the test, I found that I get a hell of a lot more of the theoretical backbone of the class than I do if I took a pre-calculus class, and I was amazed at how much of the deeper structure of the mathematics that I grasped. But I'll be damned if I could solve a triangle problem. If you handed me a test, I probably couldn't do the problems, but I understood the concept. And you're not going to remember how to do the problems 2 years down the road anyway, unless you do them every day. Goodness. But you are going to remember the concepts, and I think that's really important. So I am a real believer in auditing a class. So when they handed out the tests, I just get up and leave. I wouldn't even try to take the test because I knew I'd screw it up. So, and all the students looked at me like, you boomer.
Well, it's kind of nice to just kind of zoom out and just like, and I think it's important because if we don't start with an organizing principle of what we've learned, we actually forget it. But if we can just say, okay, this is what quantum physics is in one sentence, and it's like, okay, now I can kind of remember it, because I tend to remember things hierarchically. Right. If I could say, okay, quantum physics does this. So when it was saying this paragraph that I was highlighting in, let me show it here. This paragraph, because I was looking at good explanations of it, and it says quantum physics underlies how atoms work, and so why chemistry and biology work as they do. You, me, and the gatepost, at some level at least, we're all dancing to the same quantum tune. If you want to explain how electrons move through a computer chip, how photons of light get turned to electrical current in a solar panel, or amplify themselves in a laser, or even just how the sun keeps burning, you'll need to use quantum physics. And so I was just like, yeah, okay, now this is, some people just, it's a little bit disturbing that in some of the origins debate, they just keep focusing on kind of the really philosophical, spooky aspects, metaphysical aspects of quantum mechanics. And it kind of gives a misleading impression on that this isn't even real science. And,
I know. And not only that, but like, what is quantum mechanics used for? Like you use it in semiconductor physics to understand transistors, because you can understand why the p-n junction allows electrons to basically get through faster because of these energy bands, right? So it's the same with chemistry. So it is about calculation mostly. And I don't think you can derive ontology at a macro level from what is happening at the quantum level. I don't think there's a connection. And I've always wanted to understand quantum mechanics so that I could prove that to myself, or to find out if that intuition I have, like when people talk about spooky action at a distance and all that stuff, or a really good example is I was watching a very entertaining series called Mr. Mercedes, Stephen King. And the first season was about a detective tracking down a killer, and there was no usual supernatural bullshit going on with Stephen King. But in the second season, this guy was in a coma, and he was controlling people's minds through quantum entanglement. And I was screaming, no. Because you may get that effect where you have spooky action at a distance, or quantum tunneling at the micro level when we're dealing with the size of particles. But that effect, in order to transfer to the macro level, it would be infinitely improbable for everything to line up at the right way. And you can prove this to yourself to you. Build a brick wall in your backyard, and then start up a hill and run as fast as you can. And quantum physics says that there is a slight probability that you can pass right through that brick wall.
Yep. Quantum tunneling.
But
don't count on it.
A friend of mine famously said, but you're not a effing neutrino. If you were a neutrino, you may have a chance of passing through it. So you're not likely, because you're not a neutrino. Stop acting. Stop pretending you are one.
Yeah, so that's kind of what I get. I mean, just a little irritated. I wouldn't say terribly upset, but just irritated, because the way that kind of the philosophical, kind of metaphysical, mystical approach, it kind of denigrates what it really is. It almost treats it like this isn't real science. I'm just like, this is probably, I get the sense, I can't prove this, that if physicists had to say what's the most important discipline, the most foundational in terms of underlying physics, they'd say quantum mechanics, quantum physics. From the mathematical and understanding standpoint and historical, it'd be classical mechanics, because we tend to think classically. And so we have to, there's a lot of translating of the classical mechanics. We even use a lot of quantum mechanics uses a lot of classical mechanics type language. But I just don't like seeing this. When I hear all these philosophical discussions, they almost make it sound like quantum physics is just metaphysics. And I'm like, no, this is really serious science. But
I have a treat for you.
Yeah.
I'm sending it to you in email.
All righty. Thank you.
Pretty sure it's what you're looking for.
Oh, man, you good. You the man.
I did that while I was talking.
See, I knew that I knew there'd be something really important in hanging out with you.
Yeah, and that's probably the last important thing you'll get from me out of today. I have not been functioning for about 3 weeks, and
I know, man.
I've
been thinking of you every day, bro. So
I've been talking to my son about it, and it's really weird. The thing is, when I go through something, I've always gone through it as two people. One is a subjective observer, so I observe myself. So while I'm going through something as dreadful as what I'm going through, at the same time, I've got the scientist in me saying, what is going on with this guy? Because this guy cannot tie his shoes. and I've been having memory lapses, and I can't find words. And my son said that he was getting really concerned about me. I had to go take a COVID test, and they had like an iPhone application, and I had to go through this series of linear instructions, which were just the best instructions I've ever seen in an app, but I could not follow them. I kept getting confused and anxious, and I felt like a dawdling old person. But physical depression is something that affects a lot of people, but you do not have to add a narrative to it and let it dominate your life. You just have to outlive it. But I'm having trouble outliving it. But anyway,
I got to tell you that Bertrand Russell, when he had a lot of emotional, everyone will go through stressful times and tragedy. It's just
life.
He would actually just study. He would start trying to do math problems. He said it just calmed his nerves. So
biology is calming my nerves. Studying. Like right now, John Maddox has me studying information theory again because I got pissed off at him. But I find it very comforting to just sit down and study biology. And then last week I was studying the hormones involved, basically the enzymes involved in limb development. And I found that was the first thing I started doing after this, after my daughter died. And I would sit down and I could do it for like, I think it took me like an hour to get through one paragraph, but it was very comforting. So it's pretty cool. So I love learning is kind of my life, and it's a thing that comforts me. And I'm so happy that I didn't lose that entirely. But titled, my YouTube channel is going to hell because I can't really do videos very well right now. I want to, but I might do one later today. We'll see. But
yeah, well, you got your crew kind of helping you out. Lena joined because apparently she subscribed to this little obscure channel. Let me just explain a little bit. The reason that I'm hosting it here is this is kind of, I'm creating a new channel that's called The Wild Frontier.
Okay.
And it's just to be able to do stuff like what we're doing today. It's not going to be a polished show. We're just kind of shooting the breeze and trying to learn. Okay. So Lena asked, did I miss something? I was just reading paragraphs of what quantum mechanics is about from New Scientist.
So is Lena in the stream?
Do you want to join the stream? Come join us, Lena. Here, I'll give you a link. And I was just kind of complaining that all this stuff about philosophy and using quantum mechanics kind of denigrates the actual physics of it, because so here Lena, I'm sending you a stream, a link to the stream. So
the most important thing,
go on Speed.
Am I echoing?
Let me cut down the volume here. Let me mute myself. Go ahead, bro.
Okay, let's try again. Oh, I was echoing a little bit. Okay, the most important thing I think that's come out of quantum mechanics is understanding the periodic table and understanding why carbon forms that tetrahedral three-dimensional structure that it does. And I believe they did that work with quantum mechanics, but I'll be damned if I know how they solved that wave equation to come up with, pi orbitals and or p orbitals and pi bonds. That is an amazing, and I don't know if I think they solved it by cutting corners. I don't think they could actually do the math involved in the carbon atom, but they made progress, and I think that was important. But when you get into orbitals in chemistry, and I haven't, as it turned out, before I started talking to Immutable about 3 months ago, I hadn't touched orbitals since I was 12 years old. And I'm, and that, so how many years? 57 years or something like that. Yeah. That's a long time. So,
hey, Lena, welcome to the stream. You're going to get a real dose of nerd talk today. This is going to be pure nerd talk.
Lena's a nerd, right?
Yeah. Are you a nerd, Lena?
No, I'm not. Hi,
Well,
Mike.
Hi.
Hi,
We've had some discussions.
Mike, I just wanted to tell you that we can keep you busy. We can keep your mind busy.
Oh, you are.
You can rely on us. And
I know. Especially that little devil standing for truth. Oh my God.
yes, just rely on us. We will save you. And I just wanted to say that there are a lot of things in life that are beyond us and that we cannot understand. And you just need to accept that, Mike.
Yep. And I do. I've gotten to acceptance, like rational acceptance. I'm trying to get to the emotional acceptance. And I have never met a challenge like this where it has taken, I mean, I recover from really bad things really quickly, but for some reason I'm not recovering from this emotionally, but rationally, I think it all makes sense to me. Life makes sense to me. Tragedy makes sense to me. I just wish to hell it had happened to us, to her, so it's just, it's a hell of a thing. And I'm going to be going through basically a lot of legal stuff now and stuff with trying to get a law passed in Minnesota, basically a red flag law. So, I mean, this thing is going to complicate the hell out of my life in a lot of different ways, but it's it's taken a turn. My life has taken a turn. So, and I did not see this coming. So, but no, I have this. I'm an atheist who has unbelievable faith, and in life and in the rightness of things and the way the universe unfolds. And I was actually teaching at my daughter's graveside, I was teaching a minister about acceptance and God's will. And and he knew I was an atheist. And it was like, I had to talk with him because he was talking about, how terrible everything is and all that stuff. And I was telling him about God's will. And for an atheist to talk about God's will, well, I have a different interpretation of God's will than you guys do, but I had the same kind of faith, which is interesting, I think, don't you?
It is.
Yeah.
It is. And Mike, I'm very sorry for what happened to you.
Thank you.
I was very upset, to be honest, and I was about to send you an email, but I just, I was not strong enough to write it and to send it because I knew that you are overwhelmed with other things. And
yeah, the most common thing people have said to me recently is I don't know what to say. And don't feel that way. Send me your email. I don't care what you say. Yeah. The words I got from Praise That I Am, from Nicholas, from even Gavin were comforting and wonderful. The way your side of the fence, we're on two different sides of the fence here. Our little war, but it was wonderful how people reached out to me. And Gavin, a guy who I did not expect, did the kind of the nicest message. It was nice and short, and it was to the point, and it was wonderful. I appreciated that. So,
but you shall know, Mike. We also grieve with you, and it is genuine grief. It is not. We do not pretend. I do not pretend. I'm honest.
Yeah.
And I was really upset, really. So I just wanted to let you know. But let's change the topic because I get emotional,
Okay.
So
Quantum mechanics.
Exactly. When I think about that, I get emotional. And quantum mechanics, yeah. You know what is very interesting? How did Schrodinger come up with his equation?
How did Schrodinger come up with that equation? That's an interest.
Never explained in any of my classes.
Really?
Nobody knows.
Which is remarkable. That means it probably was quite difficult. One probably needs to learn a lot more physics to be able to understand, because some of the equations I get in physics, after my graduate program, I began to look at the history and my jaw dropped. I knew it was difficult, but it's almost a miracle these guys figured out some of the things that they did. The big one that I thought the hardest equation to solve was the one that when Planck created his Planck's constant. I look at that equation and I'm just like, yeah, he started out with an approximation, but then how he got that formula that was so precise,
yeah,
that was definitely Nobel Prize material, because that was not easy, and that was the beginning of quantum mechanics. And I'm really, I don't like calling out other colleagues, but Joel was saying to Leopolis, the black body radiation has nothing to do with quanta. I'm just like, oh my goodness, I can't believe you said that. Just don't advertise yourself as a quantum scientist if you say stuff like that. It reflects badly on our side. We have people that would say that. I just got to call them out on it. And I let a few things go, but I just had to just kind of, when I saw that exchange, I finally had to put my foot down. It's like, dude, don't do this. It ain't cool. Because a lot of people will just ordinarily trust whatever you say because you represent yourself a certain way. And so this isn't cool, bro.
Wow. So you have not watched my exchange with Joe? That was
no.
Mike.
Excuse me. Where was that?
It was on Praise Channel, and I was.
How long? How long ago? Do you have a link?
So triggered.
I know he triggers people.
Yeah, I was so triggered. I'm not the most patient person in the world, but normally I act reasonably. But this time it was so. How to say? Yeah, we need to be very, very careful not to make unsubstantiated assertions. When we make an assertion, we should be able, especially in science, we should be able to explain it to the others and not just claim something and then, that about the black holes, I didn't understand. We had an argument with Joe about in which way quantum mechanics proves God, because he uses that word proves, which I don't, which I feel very uncomfortable with, because quantum mechanics cannot prove God. It does not defy God in any way. But when we say proves God, then it is like, how to say, it sounds as if we have proved God empirically, which is impossible. Yeah, you know what I mean.
Yes. Yeah.
And then one also needs to have an understanding of quantum mechanics and be able to explain what it means. And Joe was not able to explain it, unfortunately.
He's an interesting person. Oddly enough, he and his wife had a talk with me privately about my daughter, and they were wonderful. And there's that. But then in my interactions with Joe, like when I had him on my channel, I just gave up on him. He was saying a hypothesis was the same as a theory, and he would argue. He gets a point, like his thing about Einstein being a Christian, and he will not let it go. He's a bulldog, he's a real bulldog, and he manages to really irritate people. And he has this very, the style of it, his manner of delivery doesn't help with his irritation because he's so calm about it. He's calmly explaining to you something that you just think is the most ridiculous thing you've ever heard.
Yeah.
And it drives people crazy. And anyway,
I'm sure they are a lovely family. God bless them. They have also 5 sons or so.
yeah.
God bless them. I'm sure he's a lovely father and a lovely husband. I wish them all the best, really. And I'm so glad that they were also nice to you in that moment, Mike.
Yeah, they were good. And I was pleasantly surprised. A person's true colors come out when something happens, It's interesting. How the hell did you learn to do this, Sal?
Well, actually, this is working out that you're talking, because this is how long it took for me to render. I don't know if we have a zoom feature in LaTeX, because
I can see it.
Really
I've got it up. So I've got an I, and then you put a slash, and then you put that's a backslash.
Yeah, that's Planck's reduced constant. No, I was totally listening to this, and I'm just, like I said, Joel is really nice to me personally, but he'll just say stuff, and I'm just like, I could argue with you, but I'm just not going to waste the time
to talk with him.
I have enough people to be arguing with for like the next several lifetimes, and it's just like, I don't have the time for this.
We had a thing on a little chat on a praises stream last night about the genetic code, and he said the genetic code is universal across all life, and I said, well, no, there are some exceptions.
No, it's not.
And what did he double? And then he, like right in the middle, he kind of changed the form of his argument, and I thought it was interesting, and I was too tired. I gave up. I was full of turkey, so.
I also thought that it is universal, but then Sal corrected me. And and then I stand corrected. I don't know everything, and Sal corrected me, and now I know that it is not universal. And even Craig Ventor, I think that I have seen a video with him where he explained that it is not quite universal. Yeah, we have also deviations from that.
Right. It's more universal than us evolutionists would believe it is, but it's not completely universal. So
I'll remember my first interaction with him. I was talking about quantum mechanics, and he immediately just started saying, I said, let's not assume the supernatural. Let's just assume a quantum. We can just start with quantum mechanics. He said, "Oh, that's supernatural." I'm just like, okay, I'm not going to argue with you. And he started saying, "I'm a quantum scientist." That was the work that that was the work that he did professionally. And then I see him interacting with Leophilus, and he said, "Black body radiation has nothing to do with quanta." I said, like, dude, you just total loss of credibility at that point.
Yeah, I kind of know.
Total loss.
I kind of.
Then he said, "Space, space is kind of conceptual. It doesn't have physical properties." And I'm like, "No." And then I started putting out. I said, "Okay, the free space vacuum permittivity of space," and then I gave the units, and then the same for permeability. And he said, "That's the cosmic background microwave radiation." That's like, no, dude, that is just so wrong. And I'm just like, I quit, just like.
His style is to exaggerate what he's done and what he does. He's just that type of person. And I think that's why I try to be the opposite type of person. When I start a debate, I'll start the debate out by saying, for my credentials, well, I'm a high school dropout. So.
It's the best.
Because you can only go up from there. You can't go down from there. You can't lose credibility after that.
I think that the trigger of everything was Einstein and Spinoza, and then the Trinity, and but Einstein and Spinoza was, how to say, that was the trigger of all arguments.
Yeah. Yeah.
And I don't understand why Joe insists on that Einstein was a Christian. It has no bearing, even if he were.
But he's not a philosopher, and his authority on the matter doesn't really make a difference. And then back in the 50s and 60s, the word atheist even had a different meaning. A materialist had a different meaning. And I don't know. It's unless you understand where he was coming from, and he was a spiritual person, I think, Einstein, and he got there through his physics, and that was what he needed. And Spinoza, man, books and books have been written trying to understand Spinoza. I think Spinoza was scared for his life most of the time when he wrote, so he had to be a little careful about how he labeled himself, or he would have been actually killed probably, or jailed.
He was excommunicated. How to say? Excommunicated from the Jewish community.
Yeah.
And so on. So initially he was Jewish, and initially he was religious. I think so. I suppose so. And Einstein, yeah, it doesn't matter if he were a Christian or not, but he wasn't.
Yeah.
And then Elon Musk. Then Joe also claims that Elon Musk is a closet Christian.
Oh my God.
That is just laughable.
Yep. Interesting man he is.
Yeah.
If you're wondering what I'm doing, I'm trying to figure out how come I can't, while I was listening to you, and this is why it's nice to have conversations like this. Immutable destiny. I didn't mean to ignore you. My eyes were distracted. Immutables here. If you want to, do you want to at least come by and say hi?
He would be a good person to explain orbitals to us.
Yeah.
Okay, you got
While
that.
I was listening to all this drama, I was just trying to figure out how to get some of this equations to download. So I can't find where it downloaded it as a file. So I don't know where it is. But let me show you what I want to thank Mike for. I want to show you something, Mike, and I'm really grateful that we had this discussion. You have solved a major problem here, because by you finding the solutions manual, I can self-teach now. This is like, okay, so Lena, you want to see what the study of quantum mechanics was for poor old Salvador? When I look at this, I said, each chapter was about like 2 weeks work.
Wow.
And so, yeah, this was my life. I was generating stuff like this. And so some of these problems took me hours. I think I worked on one problem. That professor, he assigned one problem, and I had the same professor for general relativity. One of the problems took 2 weeks for the class to solve. For quantum mechanics, it wasn't as bad. Sometimes I could get through it in 2 hours. But this was the class. This is all we did, just the math.
Well, if Immutable comes in, he's I think he knows how to integrate anyway, and I wouldn't know how to do that.
Well, you see, the thing that's really frustrating is there's a lot of integration with complex variables.
Yep.
And, the reason, just to explain to Lena why this looks so miserable, is that when you start dealing in 3 dimensions, the math just gets nasty. It's not so bad to deal in 1 dimension. Speaking of which, there is something that, it took me about 3-4 minutes just to type this equation out here. This is Schrodinger's equation, according to my book, but you'll see it in a different form on the internet. And that's the first problem, is the way that you see it generally stated. If you Google it, doesn't look like the way it's taught in my textbook. And I'm like, oh man, I suffered through all that math and I don't even know how the general form. But the thing that, let's see, Lena had a beautiful graph here. And this is why I also wanted to talk to you, Speed. You have the skill set to help me teach this better.
I'm doubting it. But
Lena, you sent me, I don't know, was it an email? And it had the name of that. Is that video with a girl in it? And she was showing the.
Yeah, shall I find it?
is it Hofstadter?
I'll be grateful, because this is the easiest solution to Schrodinger's equation. It's
Wait
a little.
second, but that was about one-dimensional.
Yes.
Yeah, wait a second. Give me 30 seconds.
Okay. So when they teach Schrodinger's equation, there are infinite solutions to Schrodinger's equation depending on what phenomenon we're dealing with. So the easiest is the particle in a box. And they have a whole discussion in a box. And this, ironically, it does actually deal with one particular chemical phenomenon. Let's see if they have a picture of it here. You'll like this speed of sound. Applications. There it is. The beta carotene is a conjugated polyene.
Yep.
Okay, you would know what this is because you're the chemist. But they said this is the particle in the box. And so what Lena is grabbing is actually going to show there's one part of this molecule where the electron moves around, and it will be modeled by the graph that Lena is going to show. So the Schrodinger the solution to Schrodinger's equation for not the entire molecule, definitely not the entire molecule, but it's here it is. The conjugated polyene systems can be modeled using particle in a box. The conjugated system of electrons can be modeled as a one-dimensional box with length equal to the total bond distance from one terminus of the polyene to the other. In this case, each pair of electrons in each pi bond corresponds to one energy level. See, now this is immutable destiny.
Yep.
Oh, Immutable said, I'm driving, so I can't join. Just got done Black Friday shopping. Fun, right? And Immutable said, hey, Sal, I later tonight if you're able. Unfortunately, I have a show on Evidence and Reasons. It's Seals for Jesus. And my friend Sandy Pigeon is going to be showing. He said, I can go through a derivation of you regarding the Schrodinger equation, both versions of it. He said, I've taken PChem, which is physical chemistry, so I remember some of the differential equations you need for quantum mechanics. And so thanks, Immutable. So anyway.
So basically the electron moves along those conjugated bonds. Is that what they're?
Well, I don't know the details of the chemical, but they have this particle in a box thing. And the diagrams have always been kind of misleading. Let me see if I have a picture. So classically, I don't know if I can make this bigger. There's some aspects of the diagram that are totally misleading here. Classically, if you had a free particle, say inside a box, and you weren't, this is assuming no gravity. Okay. So like, let's say this is free space, and somehow you manage to get this marble bouncing between the walls. Classically, it would look like A. So these are for classical objects. So objects that are like marbles, this works. When we get to atomic particles, this picture just totally breaks down. And that was probably what was really shocking, is then it's like it's kind of spread out all over the place.
Yep.
And it doesn't have a definite position. It does have, interestingly, it has defined, let's see, momentum. It has a defined momentum, but you can't, no, wait, no. Ooh, my professor would shoot me. It has a defined energy. Sorry.
Okay.
It has defined energy. Position and momentum are just not known, but the energy. and that's a whole nother story, because in classical mechanics, momentum and energy are really nicely tied together. I think, and I have to double check, it's different in quantum mechanics. So the diagram that I was hoping Lena would show it when it's static.
Shall I share it? Because I have posted the link in the private chat.
Private chat. No wonder I missed it. I'm sorry. Yeah, go ahead and no. Let me bring it up, because I know the spot where, because this is where I wanted Speed. He could help me, because there's some things in the way that they teach it traditionally that are just a tad. And when I first saw this, I couldn't, if they don't explain it exactly, if there's something wrong and misleading, it
this
just,
girl.
Huh?
Yeah, I'm familiar with her. She's very good.
Yeah, she is very good.
Have you watched Sabine Hoffenstetter?
Sabine, yeah.
Yeah.
I like her.
Oh yeah, she's got some great stuff. Are you familiar with that cell?
I've read her blog, and I felt kind of
Hossenfelder.
I felt kind of like upset with myself. I said I should be able to understand some of the stuff she says, and I just
she goes a little
I kind of on a superficial level, but I couldn't. It's just like, oh man, I need to really go back, because I did study some of this stuff, and I've impressed with her work and also her intellect. And she said something that was really compelling. She said, we study a lot of problems we can't solve.
Yeah.
And there are really a lot of problems. It's like, we know the theory, but the math is too difficult to solve. What they call analytically. You have to use computers and make an approximation.
Yeah.
It's not very satisfying.
She also does music videos, by the way. If you haven't seen them, they're amazing.
Wow.
I haven't seen them. I haven't seen them, but I like.
Oh, they're on our YouTube site. Watch her music videos. I played one of them on one of my streams, and I think I got a copyright. No, I didn't get a copyright strike on that one. I got copyright strikes on something else. But anyway, it was just wonderful. She does this Monty Python thing. That's just amazing. She has a voice too. I was quite surprised. But I fell in love with her, I think. And that's the only time that's happened to me in about 20 years. So it's pretty significant.
No, she's cool. Pretty cool.
Yeah.
Okay, so what I was trying to say is, you see, this is what really messed me up until I began to understand it. They say this is the one-dimensional case, and I'm like, no, this is a two-dimensional diagram. I'm just like, I'm so confused. And then I tried to interpret it for 3 dimensions, and I said, I can't visualize this in my head.
It's showing you the probability of where it will be on the x-axis, and the y-axis is just the probability.
Yeah.
So
actually, it's a little more subtle than that. You have to do you have to square it.
Oh, yeah. So the square of the probability.
The correct term is there it is. When you square it, the probability amplitude.
Amplitude, right?
And oops.
So
what's that girl's name? I don't know what her.
This one here, I'm not sure if she ever tells you. Maybe she doesn't.
Oh, okay. Well, we'll give her a name. The Quantum Babe or something.
She has credits.
So the x-axis here is the position of the electron, or the quantum, the quantum.
The x-axis is the position of the electron.
And the epsilon, is it English?
Is the probability.
Is the probability that it will be in that position.
Yeah, right.
Correct. If you just sampled it at arbitrary time. So we actually had machines that would just, I don't know how they did it. They were able to detect the position of the electron. So if we just kind of had the machine like periodically just say, okay, where is it now? Where is it now? And then you plot it, it would look it would have a distribution like this. But what I wanted to try to do, Mike, is because this accords a little more closely with the chemical diagrams, is if I had a, you see if I get a really thick line here. If I had a really, either color it or use shading. Like if it has a high probability, I'll use a really strong color. But if it's kind of like not too, I totally messed that up. Apologies. What did I do? So I don't have, I have a light shade of gray here. And then maybe a darker shade for when it is a little bit more probable. But there's a way to do this computationally so I could get kind of some nice pixels with the sine wave. Let's see. So I'm being my own clumsy self, usual clumsy self here. I'm not very good at. Sorry, guys.
You're like me when I'm drawing.
But I thought that most probably the particle is where the maximum of the wave function is on. You know what I mean? Where the maximum.
It doesn't necessarily have to be
there.
It's most probably there, but it. So like this would be, what I'm trying to illustrate is very inexactly. See, this is why I'm not very good with the with drawing. So if you have, I'm sorry, I interrupted you, Lena. What?
No, I just wanted to point out that paint is very difficult tool. It's not easy to use from my point of view.
Oh, I need to find another way to. Well, see, this is part of the reason I'm trying to learn. Trying to relearn is also because I want to not only teach myself, but I'd like to have some nice graphics. Because I went through all the trouble of learning it, and when I can draw it.
What app are you using here?
See, this is why I need Microsoft Paint.
This is Paint.
This is exactly why I wanted to talk to you, Mike, because I know you could. You see, you've already helped me immensely just by getting me that solutions manual. And I said, you're the guy who might be able to help me solve my problem of how to improve the rendering. So I'm just going to do a squiggly line here. Let me see. How do I do a free form? So if we have the sine wave here that goes up like that and down, it's nicer. If they had shown me this conceptually with just this diagram where you had kind of the intensity here, and then it's not so probable here, I would have been able to comprehend it better. Once they showed that sine wave, I got a little bit like, okay, you're talking one dimension and you're showing me a two-dimensional diagram. So something just didn't click. But when I visualized it in my head this way, in terms of intensity, I said, okay, now that correlates, and I'll show you the reason I.
Now, if you could just do it, if you did a gradient.
Gradient, that's the word.
Yes, you did
because, let me see. That is actually how they. That is how they render it.
Yep.
With gradients, and I said, now you see, because there's no way you could show that sine wave, or well, in this case, it'd be spherical harmonics.
Yep.
And actually, what kind of upsets me here is they're showing these little, in some of the diagrams, they've shown a sine wave, and just like, that's just confusing things. So when we have the, there's some beautiful pictures here. There was, they had one picture where they just used dots. Yeah, this is good right here.
Yeah.
This is a two-dimensional plot. And I said, this this kind of gives more of the spirit.
Right. Gives you a slice. Shows you the s orbitals, and I think are those p orbitals on the outside, or?
Yeah. See, this is where I'm embarrassed. See, this is where my physics stops and the chemistry has to begin, because the chemists know this. The physicists kind of know like all the primitive stuff that generates this. So just for Lena's benefit, the reason it looks kind of grainy like that, if we took like say this machine that was just recording all the positions over like a long time, this is kind of how it would render on the plot.
The actual positions.
Yes, the actual positions.
Yeah, and the only way you can find an actual position is to measure it. And when you measure it, they talk about a waveform collapse. It collapses around that point. That doesn't strike me as being anything about ontology. That's about mathematics. Because when two particles interact, if they do indeed hit each other, it is because they just happen to coincide, and then that becomes like a waveform collapse. So now we know where that particle is.
Right. So basically, what you're seeing here is that the wave function of the electron was collapsed multiple times. Every dot that's rendered, every dot that was rendered was a wave function collapse event. And you know, when I saw that, I'm like, you know, that's not really a big deal. It doesn't have to get really philosophical at that point. I'm looking for.
Yeah. What? Sorry, Sal. I have interrupted you. I just wanted to point out to Mike that, yeah, Mike, I also understood it, this wave function collapse. I also understood it as a mathematical concept,
right?
Because then we will just update the Schrodinger's equation, and the probability will be 1 in that position. Yep. This is how I understood it.
Pop up that link that I put in private chat. And,
want me to put it up?
Yeah.
Let me see. I just wanted to. Oh, here. This is what I wanted to.
Oh, the cloud.
Yeah, this is when they actually had the measurements.
Wow.
So every dot is a wave collapse, and then when they, I guess I don't know how they work this out, but basically what happens is they measure the position and they kind of let the electron keep going.
I have no idea.
So basically, it's in an uncollapsed state. So it's collapsed briefly, and then it goes back to an uncollapsed state.
That may have been a model. Did they model that, or did they actually measure?
Measure it.
How the hell did they?
I saw it in one of my science classes, and I don't remember which. Where it might have been my chemistry class, where they're showing that they were trying to plot the position of the electron over time.
Yeah.
So the reason they say the probability is 1, that just means that the electron has to be somewhere in all the universe. So there's a probability that it's somewhere in all reality. Let's just say all reality. It's somewhere. If you take all reality, but at any given time, it's most likely to be close to the nucleus. So the amplitude is all the integral of the amplitude from infinity to infinity, which really it's a triple integral for like, you know, for everywhere, for all time, it's somewhere. The probability it's somewhere is 1. So yeah, that's a better way of saying it. The probability that it's somewhere is always 1.
Always 1, right?
Yeah, it's always going to be somewhere,
right?
As long as it exists.
Yep.
So let me.
But as soon as we measure it and we detect it in one position, then the probability that it is in this exact position gets 1. And this is
that's a good point. When you've detected it, when they say the wave collapse, that means it's no longer relevant. Yeah. Basically, collapse means your equation's gone.
Yeah.
The equation no longer applies. It only applies when you're not measuring.
Yeah. Now you have an interaction. You know.
Once you have an interaction, it basically it's like you've destroyed it.
Yeah. I remember when I was 24 years old, I was parked by a lake with a girl that I had been on a couple of dates with, and I was explaining to her about quantum mechanics, and I was explaining to her that you are probably here, and she married me.
Oh, was that after the summer you had your Catholic thing?
No, that was when I was 16, the Catholic thing. But no, that my first wife was at 17, and my second wife was at 20. Probably about 20. Well, we went out for a few more years. I was at about 28. I got married the second time. So, but anyway, I think it was that quantum mechanics talk that had her marry me. So, anyway,
can you give me that line again, Speed? Try it.
You just explain to somebody how they are probably here, and you explain quantum mechanics. And I remember doing it with my steering wheel, explaining to her why the steering wheel was probably here. Like if you look at this orbital diagram, okay, these p orbitals here. For one thing, this is how they show p orbitals, but they do it that way. This is kind of a graphical, what would you call it? They've taken license with it a little bit, because the actual p orbital looks a little rounder than that, I think, but this is like the most concentration. But anyway, these bonds, okay, when you take a p orbital and you combine it with an s orbital, which is a sphere, you'll end up with this hybrid orbital thing, and it gives you the tetrahedral bonding of a carbon atom. Now, that is something that exists at a very, very tiny quantum level, right? Yet it has the effect of making us what we are as biological animals. That tetrahedral structure of carbon, when you put enough of them together that you have an actual chunk of something, some organic compound, it makes a big difference. So the quantum probabilities end up manifesting themselves in our macro world, which is very interesting. So, but basically, it's with these orbitals that they determine at what angle a bond will form with another, between two atoms, and between carbon atoms, it's tetrahedral, and it has its structure. And then if you add a double bond, you end up with a sp2 orbital. It's a hybrid. But anyway, they work all this out with the Schrodinger equation, I think, and I have no idea how they do it. And like I say, it was, other than my immutable trying to reteach this stuff to me, and him and I, him being the teacher and me being the student, we're like oil and water. We don't work together. But other than that, it's been 57 years since I looked at this stuff. And back in the day when I looked at it, the chemistry books did not use it as much as they do today. They use orbitals in organic chemistry more seriously than they did back in 1964, whenever I ran into it. So it was a while ago. But anyway, the point I wanted to make is that these probabilities end up launching themselves into our macro world, into our lives. And this is how organic molecules work. And this is how biochemistry works with these shapes. And but what you gotta, we lost Lena?
No, I was.
Okay. You're doing.
I was going to answer your rhetorical question. How did they figure this out?
Yeah.
The mathematician. That's chapter 4 in Griffiths' book.
Oh my God, I'll never get there.
And that's,
life is too short. Okay.
Yeah. So that's chapter 4, and actually,
that's what they do.
they had some mathematician. That's why you need teams of scientists to do it, because there's no one guy that's going to do it. Not even Einstein.
Yeah.
He had to consult mathematicians to help him. So someone had worked all this out. The math.
Oh, nice.
Sometimes the math problem was already worked out. You just have to meet the mathematician that knows it. So probably these guys found some professor and said, "Can you tell us how to? We have this equation, but we need need someone to tell us how to draw this up for this situation." And in fact, the name, the solution is probably found even before quantum mechanics, because there's a name associated with it. It's called the Legendre polynomial.
Okay.
And so just like with relativity, the math had been worked out even before they encountered the physics problem, which is kind of spooky if you think about it, because this is when mathematicians tend to find things out in their research. Then around that time, they begin to find the physics problem that it was meant to solve.
Right.
Which is really cool.
I started sketching out a polynomial theory of evolution the other day, basically, or cell biology using polynomials. And I'm on to something, and I'm going to keep working on it. But
alrighty. But to answer, if I could go back to this diagram here, this to my eye, that looks like a s orbital, that spherical orbital. But you can see it's clearly not orbiting. I mean, where do you draw the circle or the sphere?
Yeah.
That's purely arbitrary that you make it look like it's exactly this distance. You can say it's the mean. You can come up with the mean distance, and that's what you call it.
If you took 1 billion points and plotted them, you would end up with a gradient, and the s orbital would get weaker, like with your gray at the outside, and it would just be a gradient from that center, and that center would be very highly probable or more probable, and then as it moves out, but it's amazing. But then when you think about the carbon atom being in that tetrahedral stereochemical formation, what you also have to understand is that thing is like jiggling around all the time. So it's always jiggling because of this probability thing. So it's always moving, depending on how much energy there is. And it's just that the most probable thing is for something to happen a certain way. And at the macro level, those probabilities multiply to the point where you can say, I am probably here. This is probably going to happen. And when you say probable, you mean for certain, almost.
But I wanted to point out something. Once you've observed something and measured it, it's already in the collapsed state.
Yeah.
So when you're telling your eventual wife that she was probably there, the odds were probably already 100% because she was in a collapsed state. It's just like Schrodinger's cat.
Right.
Once you're observing it, she's probably already collapsed.
Yep.
So at least you didn't tell her she's collapsed. That probably wouldn't have gone over well.
No, I didn't tell her that. That probably would have ended the relationship. But anyway, it's amazing. Both of my wives were, or all of my relationships, they always start out saying, "Oh, it's so fun to listen to you talk about science." And then after 4 months, they say, "I'm so goddamn sick of you talking about science." The thing that attracted them becomes the thing that repels them. And I've had two or three women tell me that that their next relationship, they're going to find the dumbest guy they can find because they had such a bad time with me. I've heard that 3 times. I'm like, okay.
This was, by the way, Speed, this was a very constructive discussion. I had a feeling if I talked to you, so that's the fact you helped me find that solution manual.
That's the only good thing I've done here.
Well, the other thing that I was talking about is you could see now that when we had Lena's the diagram from that woman.
Yep.
Here, you see this is what threw me off is I was seeing this here, and then I was seeing the gradient diagrams. If I could kind of superimpose this with kind of something like this, then it would make
more sense.
It would kind of resolve my cognitive dissonance there.
Yep.
And I said, you probably know how to write a program to draw that.
I probably could.
Yeah.
I'm thinking.
Yeah. So just think
Python.
on it. I mean, I could probably write one. I was a software engineer many years ago. I've totally lost all those skills.
So you want a gradient that basically, like that line on the bottom, you want it to be a gradient that follows the sign distribution.
The sine squared distribution. So
sine squared distribution.
Yeah.
Okay.
So that would be, you got it right here. See, and the sine squared distribution over one cycle.
Yep.
And
let me think on that.
Yeah, because that's how we can actually visualize it. And then if I were teaching myself, it would kind of even relate to this here. But you see, there's just as an FYI, why doesn't this look like a sine wave? Because you have a charge here. The nucleus is positively charged. The particle in box doesn't have any forces acting on it.
Right.
And so that changes the solution to the Schrodinger equation.
So from that, can they calculate that beta carotene is red or orange? I'm not sure.
I don't know.
So
You see, that's really cool. They're all this. This is why I was fascinated by biophysics. There are all these interesting questions.
Yeah.
And I don't, I don't want to get into a fight here, but I would much rather study biophysics than, say, evolutionary biology. I just find they're really interesting questions. And
they're the same thing, so.
Okay, we're not going to fight. All right, we've done it.
Okay.
All right, we're not going to fight. So anyway, this was very productive, and I got to see how difficult it was to also render some of the equations. But now that you got some of the equations for me, that's going to be a big help. But one thing that was really helpful that I'd like to eventually do is Richard Feynman used to use colors. Well, he had a certain condition or gift called synesthesia.
Yep.
So numbers would have different colors, and he could visualize numbers with different colors.
I have a problem with that too. I have behind me, I have probably 1,000 or maybe 2,000 different colored pencils. And I have, in order for me to understand anything, I have to break it into one-liners and I have to color it. And I've never understood why.
Well, see, Feynman just did that in his head, which is remarkable. And I've been trying to look at equations in terms of colors too.
Yeah.
And if I could colorize some of this, it's easier to see the relations.
Right. It is.
It just kind of leaps out, because in black and white, and I realized, I said, I could understand this if it's colored. And just like a real simple application, because we think a lot of the math is done in 3 dimensions. It almost makes sense. Oh, well, yeah, a lot of the math is 4 dimensions, X, Y, Z, and time. Yeah. And when you can identify the parts that are dealing with like X versus T, and you color it out, it starts. I started trying to do that with the LaTeX in Microsoft Word. And I said, this is really powerful. You could actually see. I said, no wonder Feynman was able to do math so well. He could actually see it in his head.
Yeah. That was like when I was in high school chemistry, or I think it was, I think we had it was a science class, and all of my classmates were just bored out of their minds. But when I saw the chemicals, I saw them in 3D multicolored. Like these videos that they show now, I have been waiting all my life for those videos, because those things were in my head when I was a kid. And it was, and that's how, I would try to explain to them how wonderful chemistry was, and they would, nerd out on me, or classify me as a nerd and put me in that box, And back in the 60s, being a nerd didn't work very well. It worked on my second wife, though.
So before we close, I wanted to read this passage here. Okay. I found it when I was just kind of doing some self-study. And it was, oh boy, did it blow up my, it blew up my
computer.
It blew up what I was trying to show. See, here it is. Hang on, let me show it again. It said the covalent bond in quantum mechanics. It said the behavior of electrons in molecules and atoms is described by quantum mechanics. Classical Newtonian mechanics cannot be used because the de Broglie wavelength of the electrons are comparable with molecular. Well, I don't need to go there, but then he describes all this in terms of quantum mechanics and why it describes a covalent bond. And I was like, okay, that's kind of grounding me back into what quantum mechanics really is. And because when I was preparing my talk for Lena last week, or no, was it just 2 days ago? Was it only 2 days ago?
It was 2 days ago. Mhm.
Oh boy, time. Oh my goodness. It seems like so long ago. A lot has happened in just 2 days. I was saying, how could I explain this? Because I was trying to go away from the philosophical aspects. I felt it was important to show that this is bedrock science. And I began looking up covalent bonds in quantum mechanics. And I said, yeah, I'm on solid ground to say that it helps us understand chemistry.
Yep.
So that was all I had for today.
Okay.
And now I can go back to, as you could see, that was great that you showed that solutions manual.
Yep.
Most of what I did in the quantum mechanics class was not actually understanding quantum mechanics in terms of what it was.
Problems.
It was just, I was just like, oh my goodness, what am I doing here? All I'm doing is just all these derivations.
Yeah.
And because I had a math background, I could manipulate. I was just manipulating symbols for hours. And just like,
that's kind of a problem with our education system is we teach ciphering first. We teach the kids how to cipher. We don't teach them the relationships and the why. And, I think we should teach imaginary numbers and sine waves and things early on, but in an intuitive sense. And once they have the intuitive sense, they will have the drive to learn how to cipher if they need to. But most of the time, we don't. I mean, nobody's going to work this stuff out.
And that's one reason that, now coming to chemistry, now that I'm trying to learn a little chemistry, this is why this became more, what you're saying is about relations, I'm going to show a diagram. And this is something, if we solved this through quantum mechanics, it would be painful, but we solved it kind of, I actually think we solved this with crystallography or some sort of technique.
We did. Yeah.
We could use Schrodinger's equation to describe the structure, kind of the way that water molecule is laid out, where you have the hydrogen atom here.
Yep.
Here with the oxygen. I kind of like the other way around because then it looks like Mickey Mouse, with the ears.
Yeah.
The hydrogen's the ears, and that's Mickey Mouse's face. So I don't know. That's just the way I
watched a really fascinating video on the cell and protein folding, and water, it turns out, has a lot to do with how proteins fold. And basically at the level you're thinking and looking at it, the cell is like this big gel, like a jello, and water is that gel that surrounds everything, and it has an amazing effect on protein folding and how proteins fold. And this is there's some current research on this that they're doing that is pretty fascinating. But trying to imagine what's really in a cell is difficult for us smart apes. See what I did there, Sal?
I did. Primate is fine with me.
Okay.
So the reason we do a lot of experimental stuff is we can't actually, some of the molecules are so complicated, we just have to look at them. We could try to solve their structure with Schrodinger's equation, but someone told me, he said, yeah, you give up after just a few molecules.
I think
we don't have the computer power to figure out the shape. It's just better to kind of slap them together and then look at them.
Yeah, I don't think they've made it as far as carbon yet, actually, other than with approximation. So
yeah. And then the other thing is that there's dynamics, meaning there's vibrations and stuff.
Yep.
It's like springs. But I guess it was satisfying to the physicists to know that they had the equations. It's just frustrating because they know they're not going to solve anything that's beyond trivial at this point. We don't have.
You can tell a lot from the structure of the equations, once you wrap your mind around them,
So.
Okay.
Lena, do you have any last words? I hope you had fun hanging out with the nerds.
I had no idea that we can use the Schrodinger's equation to find out the structure of the molecules.
Yep.
Yeah, you see, this is what then it was worth it to show some of this, because now you could see why I mentioned in our talk 2 days ago, I said, at least, some estimates are 1/3 of our economy are based on quantum mechanics. It's like hardly anyone knows what it is. And just because it is so tied to chemistry, that's a big reason in and of itself.
Yeah, the shapes of those molecular machines that Otangelo talks about, and you talk about cell, all come down to this Schrodinger's equation eventually. So.
Yep. And that's why I look forward to working with Change Tan. She was a physical organic chemist, so this is her, trying to use both quantum mechanics and then kind of just peering into the molecules and principles to figure out their structure. Just incredible. So I'm glad you had a good time, Lena. It's always.
Thank you.
Yeah.
Mike, thank you.
You're welcome. Thank you for showing up.
Yeah. Hope you had fun, Mike. It was great hanging out with you again.
Yeah, let's go backstage for a minute.
All right, going backstage. Okay. And to any of the viewers looking at this recording, thank you very much for your time. Take care.
Take care. God bless you.
Yes. God bless you all.